Today we cover section 4.2, an introduction to voting. Might better be described as an introduction to voting methods. But before we go any further, almost everything we do in this section requires us to read a preference table. Sometimes it's called a preference schedule. For that reason, let's take some time to learn how to do just that before we move forward into the material. Suppose Alice, Bob, Carol, Don, Ellen, Frank, Gina, and Helen are asked to rank the seasons of the year in the order they prefer them. 1 is their favorite season, while 4 is their least favorite season. Here are the results. Alice thought that fall was the best season, winter the second best, summer the third, and spring was Alice's least favorite. Also notice that some of these ballots are identical. For instance, not only did Alice think that preference was right, so did Carol and Don. All 3 of those ballots had fall as their favorite season, winter second favorite, summer third favorite, and spring as least favorite. I would like to condense that down into a more readable format. So I will list that fall, winter, summer, spring, but I'll give it a count of 3 to indicate that 3 ballots gave that exact preference ranking. If you look a little further, you'll notice that Bob and Ellen also agreed perfectly. Both Bob and Ellen thought fall was the best season. They thought spring was the second best season, followed by summer, and winter being the least favorite season for them. So I'll write that down and give it a count of 2 to indicate that 2 voters had those exact preferences. Continuing to look, Frank had a unique preference. Frank thought that summer was the best season, followed by winter, fall, and spring, and no one else had that exact preference ranking. So I'll list that, but give it only 1 vote. Finally, both Gina and Helen preferred spring, followed by winter, followed by summer, with fall as being their least favorite season. So if I list that, I would give it a total of 2 to indicate that 2 voters had that exact preference. This is a preference table. It is an efficient way of summarizing a group of individual preference ballots, and it just makes it easier to look at the results in a more succinct form rather than looking at each individual ballot. And we'll be doing a lot of these preference tables, so it's good for you to understand where they came from. Now that we know how to read and interpret a preference table, let's move on to a more in-depth discussion of voting methods. Here we're going to discuss different voting methods and the fairness of each. Although there are many others, we'll just cover 4. The 4 voting methods we'll cover are plurality, Borda count, plurality with elimination, and pairwise comparisons. Let's look at each one of these one at a time, starting with the plurality method. In the plurality method, each voter votes for one candidate, and the candidate with the most votes wins. The winning candidate does not have to have a majority, which would be more than 50% of the vote, only the most votes. So for example, if Alice got 30% of the vote, Bob got 40% of the vote, and Charlie got 30% of the vote, then Bob would win, even though Bob does not have a majority of the vote. There's a potential fairness issue here, and that is, if Bob wins with 40% of the vote, he did not have a majority of voters behind him. Let's take a more sophisticated example. Suppose there are 4 types of chocolates, and a group of children are going to list their preferences. 1 stands for the best, that's the one the child thinks is the best, and then 2, 3, 4 would be the worst. This table gives Kit Kat, Snickers, Hershey's, and M&M's, and it gives the preference table for that. And you can see, if you look at the number of voters at the bottom, there are 17 voters that had the same preferences, another 11 that had the same preferences, another 9, another 8, another 3, another 2. In other words, these children are considered to be the voters in this case. The question is, using plurality voting, which chocolate is the children's favorite? Now, how do you read this preference table? Well, we talked about that a little earlier, but in particular here, if I look at that first column, it tells us that 17 children ranked Kit Kat 4th, Snickers 1st, Hershey's 3rd, and M&M's 2nd. And you can go down the columns similarly. Remember, plurality voting only looks at first place votes, so most of this information in this preference table is irrelevant when we're using the plurality method. So you simply look at first place votes. So I'm going to build a table that lets me count how many first place votes the Kit Kat got, the Snickers got, the Hershey's got, and the M&M's got. So I'm looking through, let's start with Kit Kat. If I scan through the first row, which is the Kit Kat row, there are absolutely no first place votes for Kit Kat. So that's a 0. Moving to the second row, which is Snickers, there are some first place votes. If I look, 17 children voted Snickers first place. But that's it. Moving to the third row, Hershey's, there are 11 children and 9 more, for a total of 11 plus 9, 20. So 20 children voted Hershey's first place. And finally, moving to the M&M row, 8 children in the third from the last column, another 3 children in the second to the last column, and another 2 in the last column, 8 plus 3 plus 2. So another 13 children voted M&M's first place. Notice the second, third, and fourth place numbers don't matter at all in plurality voting. So who wins? Hershey's is a plurality winner because Hershey's had 20 first place votes, more than anyone else. The second of our voting methods is the Borda Count method, and it does take into account more than just the first place votes. Instead of just first place preferences, each voter's full set of preferences is considered. If you want to describe the process in words, you could say something like this. If there are n candidates, each voter gets n points to their first choice, n minus 1 points to their second choice, etc., etc., etc. Do you finally get down to the least favorite candidate getting 1 point? And the candidate with the most points wins. Let's go back to our chocolate example, Kit Kat, Snickers, Hershey's, and M&M's. Using Borda Count voting, which chocolate is the children's favorite? Now, there are numerous ways you can do this. I'm going to show you one way here, and later on I'll do another example. It sort of gives you a variation on that. You need to practice this the way that makes most sense to you, and I'll leave that up to you. But I'll show you a way here, and then I'll do another later that does a slightly different process. And you pick the way to do it that makes most sense to you. In any case, Borda Count involves a calculation that's a little bit similar to doing a weighted mean. The votes are sort of like the values and the points are sort of like the weights. It's that sort of thing. It's not an exact analogy, but it's sort of like that. So let's do this. What I'm going to do is build a table for each calculation. I'll do a calculation for Kit Kat, a calculation for Snickers, a calculation for Hershey's, and a calculation for M&M's. So I'll build a table for Kit Kats. What I need is a column for the number of votes. Then I've got a column for how many points you get for that vote. And then I've got a column where I'm going to multiply the votes times the points. And I'll do that for Snickers and Hershey's and M&M's as well. Complete that table for each chocolate. First thing I do is notice that the points are going to go down 4, 3, 2, 1. First place is worth 4 points. Second place is worth 3 points. Third place is worth 2 points, and fourth place is worth 1 point. So I can go ahead and get that filled out. Then I'm going to look at the votes. Let's just start with Kit Kat because it's the first row. I'm looking at the first row for Kit Kats, and I notice that there aren't any first place rankings. That means Kit Kat gets 0 first place votes. But I do see some second place votes. Kit Kat actually gets 3 second place votes. There are a couple of places where Kit Kat gets third place votes. There are 11 in the second column and 8 more in the fourth column. 11 plus 8 is 19. So Kit Kat gets 19 third place votes. And then there are a couple of 4s. In fact, there are 3 4s. 17 plus 9 plus 2, which is 28. So Kit Kat gets no first place votes, 3 second place votes, 19 third place votes, and 28 fourth place votes. Now let's move on to Snickers. Snickers is the second row. I'm scanning for first place votes. Snickers only gets 17 first place votes. Second place votes, there aren't any. So Snickers gets 0 second place votes. Third place votes, 9 plus 2, it's 11 third place votes. And fourth place votes are 11 plus 8 plus 3, which comes out to 22. So Snickers gets 17 first place votes, no second place votes, 11 third place votes, and 22 fourth place votes. Moving to the third row for Hershey's, there are 11 plus 9 first place votes, that's 20. Going to looking for second place votes, 8 plus 2, there are 10 second place votes. There are 17 plus 3, which is 20 third place votes. And finally, you notice that there are no fourth place votes. So Hershey's gets 20 first place votes, 10 second place votes, 20 third place votes, and no fourth place votes. Finally, the M&M row, scan for the ones. That's 8 plus 3 plus 2. That's 13 first place votes. Now scan for the second place votes. That's 17 plus 11 plus 9. That's 37 second place votes. And notice that M&M's doesn't get any third or fourth, so that means there are 0 third place votes and 0 fourth place votes. Once you get this done, all you have to do is complete the votes times points columns and you're practically done. So I want to multiply across. Going back to the Kit Kats, 0 times 4, 3 times 3, 19 times 2, 28 times 1. So the votes times points column for Kit Kats are 0, 9, 38, 28. Do the same thing for Snickers. 17 times 4, 0 times 3, 11 times 2, 22 times 1. That's 68, 0, 22, 22. Moving to the Hershey's column, that's 20 times 4, 10 times 3, 20 times 2, 0 times 1. That's 80, 30, 40, and 0. And finally, for the M&M's, 13 times 4, 37 times 3, 0 times 2, and 0 times 1. That's 52, 111, 0, and 0. And then you just add up those products. So in each of those 4 product columns, you just make a sum. The sum of the product columns is the Borda Count number for each chocolate. It turns out if you add 0 plus 9 plus 38 plus 28, you get 75. If you add 68 plus 0 plus 22 plus 22, you get 112. If you add 80 plus 30 plus 40 plus 0, you get 150. And finally, you get 163 if you add 52, 111, and 0 and 0. So by the Borda Count method, you can see that the M&M's wins with 163 Borda Count points. Before we move on to a third voting method, I want to take some time to think about the plurality versus the Borda Count in a particular way of thinking. Suppose 2 students are competing for a merit-based scholarship. If student 1 has 3 A's and 3 F's and student 2 has 2 A's and 4 B's, which student do you think is more deserving of the scholarship? Think about that for a minute. Which student, if you had to pick one of those 2 to give the scholarship to, which do you think you would choose? Interesting question. If you just look at who has the most A's, you would choose student 1 because student 1 has 3 A's, student 2 only has 2 A's. That's sort of like the plurality method. The plurality method only looks at the top level preference. That's sort of like looking only at the A's that a student has. On the other hand, if you computed each student's GPA, you would find out student 2 has a better GPA than student 1. That's considering all the students' grades, not just the highest grades. That's sort of like the Borda Count method. So as you're going through these and comparing them and thinking about how they work, the plurality method only considers the top level, the first preference. The Borda Count, though, blends them all in. And you got to think, which is a better way to do it? It seems to me that using more information, which is what Borda Count and calculating the whole GPA does, is a little bit more fair than just looking at how many A's someone has. Again, fairness is in the eye of the beholder, but I think most people would agree with that, actually. Anyway, on to our third method of voting, that's plurality with elimination. This one is a multi-stage process. What you do is you eliminate the worst candidate at each stage. You just take the plurality method you've already been using, do it, and then whoever gets the least votes gets knocked out, and then you start over. And you keep going until there's only a winner standing. If you had to describe this as a process in words, you might say something like this. Step 1 is to eliminate the candidate with the fewest first place votes. Step 2 is to shift the preferences for the remaining candidates so that they correspond to how many candidates are actually left. And then the third step is just to go back and repeat the process until you're down to just one winner. And of course, the best way to illustrate that is through an example. Let's do that children's chocolate preference problem again. This time, let's do it with plurality with elimination. So we're back to the same preference table that we've seen before, Kit Kat, Snickers, Hershey's, and M&Ms. This time we're going to do plurality with elimination, which means we run a plurality election and eliminate the worst. Well, we've sort of already done that stage. We've got to eliminate the candidate with the fewest first place votes. And remember, with plurality, you only look at the first place votes, but we really already did that. We found out that when we first started before that Kit Kat didn't get any first place votes, and the other three did get some. So in running this plurality with elimination, we can take advantage of the fact that we really already did the plurality election once for this problem. So we already know that Kit Kat is the first one eliminated. So we can get rid of Kit Kat. Second step is to shift the preferences for the remaining candidate. And what that means is there are only 3 candidates left, Snickers, Hershey's, and M&Ms, but you've got some numbers that say 4. Well, there aren't any 4s anymore because there are only 3 left. So what you need to do is go back in there and make sure every column is labeled 1, 2, 3. So if you see that 4 in the second column, that really should be a 3 because there are only 3 candidates, in this case chocolates, left. In that third column, you've got 1, 2, and 3, you're okay. In the next column, you need to change that 4 to a 3, and in the next column, you got to be careful here. The 4 becomes a 3, and the 3 becomes a 2, because 3 is a better ranking than 4. 1 is the best, so that 4 becomes a 3, the 3 becomes a 2, and the last column is okay. So that's what I mean by shifting the preferences for the remaining candidates. If there are only 3 candidates left, all your numbers should either be 1, 2, or 3. Okay, once I've got the preferences renumbered, I run another plurality election. So you go through there and you look, do it again, and see what happens. I know that Kit Kat's already out. I've only left with Snickers, Hershey's, and M&Ms. Running this election again means counting first place votes for each of the remaining chocolates. So I want to go through and find the first place votes for Snickers. Well, looking at the Snickers row, there are 17. Then I want to go and look at the Hershey's row and look for first place votes, and there are 11 plus 9, which are 20. And finally, I want to go to the M&M row, and I'll notice that there are 8 plus 3 plus 2, which is 13 first place votes for M&M. So in the plurality with elimination method, the least votes goes out. That would be M&M's with 13. So in the second stage of this process, M&M's gets eliminated. So now we're down to Snickers and Hershey's. So you move to step 2, which is to shift your preferences for the remaining candidates. In other words, there are only 2 things left, Snickers and Hershey's, so your numbers should all be 1 and 2. So if you're looking back through there aren't any 3s anymore because all you're left with are Snickers and Hershey's. So 1 stay 1, but anything that's not a 1 is going to be a 2. So if you look through there, in the first column, that 3 becomes a 2. In the second column, that 3 becomes a 2. Then in the third column, that 3 becomes a 2. In the next column, the 2 becomes the 1, and the 3 becomes a 2. And then in the next to last column, the 2 becomes a 1, and the 3 becomes a 2. And in the last column, the 2 becomes a 1, and the 3 becomes a 2. Remember, all you can number now with 2 candidates left are the numbers 1 and 2. So the lowest number becomes a 1, and the highest number becomes a 2. Okay, now we've got our preferences shifted again. We need to go back and count. All that's left is Snickers and Hershey's. So I want to go through there and eliminate the one with the fewest first place votes. Before I can do that, I have to count the first place votes. So, starting with Snickers, go to the Snickers row and look for ones. There are 17 first place votes for Snickers. Then go to the Hershey's row and count first place votes. Well, there are a whole bunch of them. 11 plus 9 plus 8 plus 3 plus 2. That adds to 33. That immediately tells you Hershey's is the winner, the only one left standing, by plurality with elimination. The last method is called pairwise comparisons. This is a head-to-head method where each candidate is matched one-on-one with every other candidate. In other words, you pick 2 and run them against each other and see who wins. Then you pick another 2 and you run those 2 against each other and see who wins. You take every combination of pairs of candidates, run them against each other, and see who wins. The process formally is this. When matching each candidate pair, you give 1 point for a win, a half a point for a tie, and no points for a loss. And the candidate with the most points wins. Let's do that with the chocolate example again. Back to the Kit Kat, Snickers, Hershey's, and M&M's. We're going to pair the candidates 1-to-1, so you first have to figure out what all the pairings are. So let's list those head-to-head matchups. And you need an organized way of doing this. I would just start with Kit Kats and pair it with everything else and then move down to Snickers and Hershey's and then M&M's. So for instance, if I want to make a matchup column, the first thing I might do is match Kit Kat to Snickers. Then I'd leave Kit Kat in and match Kit Kat against Hershey's, and then leave Kit Kat in and match Kit Kat to M&M's. That's every match that would involve Kit Kat. So now I'll move down to Snickers. I could match Snickers with Hershey's. I could match Snickers with M&M's. And now the only thing I haven't matched is Hershey's with M&M's. So if you do this in an organized fashion, you can very easily list all the head-to-head matchups. Now you've got to see who wins those head-to-head matchups. So let's do that. At this point, it's useful to notice that there are actually a total of 50 voters, or 50 children expressing their preferences, because the number of voters in that bottom row, 17 plus 11 plus 9 plus 8 plus 3 plus 2 is 50. Now the reason it's useful to know at this point is that with these head-to-head matchups, a chocolate has to get more than half the votes to win. So I know that if any candy can get 26 votes or more, that candy is going to win. So I can stop counting at any point that one candy gets at least 26 votes. So that's useful to know. Now let's do these head-to-head matchups. Let's start up on the left with Kit Kat and Snickers. So I'll make a little matchup table for that. Kit Kat versus Snickers. Look back up. I cover up the other 2 because it's distracting. I'm just looking at Kit Kat versus Snickers. And in that first column, I see that Kit Kat had a preference of 4 and Snickers had a preference of 1. So those 17 children preferred Snickers to Kit Kat. So Snickers wins with those 17 voters. So I give those 17 votes to Snickers. Now keep moving across columns. In the next column, Kit Kat gets a 3 and Snickers gets a 4. 3 is better than 4. So Kit Kat wins with those 11 voters. So I give 11 votes to Kit Kat. Keep moving across. In the next column, Kit Kat gets 4, Snickers gets 3. 3 is better than 4, so Snickers wins that with those 9 voters. So I give those 9 votes to Snickers. And at this point, I can notice that 17 plus 9 has already gotten to 26. I could keep going if I wanted to, but 26 is over half the vote. So I know at this point that Snickers is going to win, and I can just stop and say that Snickers has won and give that match to Snickers. I don't have to go all the way across if I notice that Snickers already has enough votes to win. And then you do this for the others. So now I go to the Kit Kat versus Hershey's matchup. And again, I'm just going to cover up the other two chocolates because I'm only concerned with Kit Kat and Hershey's. So I start over again and look at those two. In the first column, 3 beats 4, so Hershey's wins those 17 votes. So I give those 17 votes to Hershey's. In the next column, 1 beats 3. I give those 11 votes to Hershey's. And at this point, I notice again that 11 plus 17 is already 28, so Hershey's has already won this. I don't have to keep going. So I'm going to go ahead and declare that race over, and Hershey's won. So I can move on to the next matchup. The next matchup is Kit Kat versus M&M. I cover up the other two chocolates because I don't care about them at this point, and I start over with the first column. 2 beats 4, so those 17 votes go to M&M. Moving on, 2 beats 3, those also go to M&M's. And I notice that 17 plus 11 is 28. That's again already more than half. I just have to get to 26. So I can go ahead and declare this election over, and M&M wins. Next is Snickers versus Hershey's. If you look in column 1, you'll see that 1 beats 3, so Snickers wins. 17 votes. Next, 1 beats 4, so Hershey's wins 11 votes. The next column, 1 beats 3, so Hershey's wins again, 9 votes. In the next column, 2 beats 4, so Hershey's wins 8 votes. And at this point, you might notice that 11 plus 9 plus 8 is equal to 28. That's more than half of the 50 voters, so I can say now that Hershey's is the winner between Snickers and Hershey's. The next matchup is Snickers versus M&M's. If you look at that, 1 beats 2, so Snickers wins those 17 votes. In the next column, 2 beats 4, so M&M wins and gets those 11 votes. In the next column, 2 beats 3, so M&M wins again those 9 votes. In the next column, 1 beats 4, so M&M's wins yet again those 8 votes. And if you notice, 11 plus 9 plus 8 is 28, and that's more than half. You only need 26 to get a majority. That means that M&M's wins the matchup and move to the last matchup, which is Hershey's versus M&M's. In the Hershey's versus M&M's matchup, 2 beats 3, so M&M wins those 17 votes. In the next column, 1 beats 2, so Hershey's wins those 11 votes. In the next column, 1 beats 2, so again Hershey's wins those 9 votes. In the next column, 1 beats 2, so M&M wins those 8 votes. In the next column, 1 beats 3, so again M&M wins those 3 votes. And if you notice, 17 plus 8 plus 3 is equal to 28, so M&M wins the Hershey's M&M's matchup. And those are all my head-to-head matchups. Now I'm ready to do my tally. Remember, the final tally is 1 point for a win, half point for a tie. If you look at these, Kit Kat won absolutely none of the matchups, so Kit Kat gets 0 points. Snickers won one of those matchups and gets 1 point. Hershey's wins 2 of those matchups and gets 2 points. M&M wins 3 matchups and gets 3 points. So M&M wins more matchups than anyone else. So by pairwise comparisons, the winner is M&M's. It's fairly straightforward. Do have to be careful. Just for fun, let's do one more Borda count. I told you earlier that I was going to do another Borda count and do a slight variation on how I did it before, just to give you some options, because some people like to do things one way, some another. but be careful and pick the way that makes the most sense to you and stick to it. So this is just a slight variation on the previous method. Choose whichever way makes the most sense to you. Here's the problem. A kindergarten class was surveyed to determine the children's favorite cartoon characters among Mickey Mouse, Bugs Bunny, and Scooby-Doo. The students ranked the characters in order of preference. The results are shown in the preference schedule below. So you've got Mickey Mouse, Bugs Bunny, and Scooby-Doo, and the number of students is listed at the bottom, just a standard preference table or preference schedule. We want to use the Borda Count method of voting to determine the children's favorite cartoon character. So the process is, there are 3 candidates here. Each voter gives 3 points to their first choice, 2 points to their second choice, and 1 point to their third choice, and the candidate with the most points wins. So to start off, let's just count each character's votes. I'll make a table, and I'm going to list the characters as rows, Mickey Mouse, Bugs Bunny, and Scooby-Doo, and then I'll have a column for first place votes, second place votes, and third place votes. So I'm just going to count those. Let's start off with Mickey Mouse and look at Mickey Mouse's first place votes. If you look, Mickey Mouse has 2 ones in the Mickey Mouse row. One represents 6 votes and the other represents 4 votes. That's a total of 10 votes. So Mickey Mouse gets 10 first place votes. Now let's stay with Mickey Mouse and let's look at second place votes. There are 2 twos in the Mickey Mouse row, one representing 4 votes and the other representing 4 votes. 4 plus 4 is 8, so Mickey Mouse gets 8 second place votes. Finally, look at Mickey Mouse's third place votes. There are 2 of those as well. One 3 represents 4 votes, the other 3 represents 10 votes. 4 plus 10 is 14, so Mickey Mouse has 14 third place votes. Now move to Bugs Bunny. Let's first look at Bugs Bunny's first place votes. There are 2 ones in the Bugs Bunny row. One represents 4 votes, the other represents 4 votes, and 4 plus 4 is 8. Now look at Bugs Bunny's second place votes. There are 2 of those, one representing 6 votes and the other representing 10 votes. 6 plus 10 is 16. And finally move to Bugs Bunny's third place votes. There are 2 threes as well, and both represent 4 votes, so 4 plus 4 is 8. Now we need to move to the last, which is Scooby-Doo. Look at the first place votes. There are 2 ones, one representing 4 votes, one representing 10 votes. That's a total of 14 votes for first place for Scooby-Doo. Now move to second place. There are 2 twos, both represented by 4 votes, so that's 4 plus 4 is 8 votes. And finally, there are also 2 threes, one representing 6 votes, one representing 4 votes, and 6 plus 4 is equal to 10. So Scooby-Doo gets 10 third place votes. Now that we know how many first, second, and third place votes each has, we just have to multiply all the first place votes of each character by 3, each second place by 2, and each third place by 1. So the structure of your products will be, you can see the character points is 3 times the first place votes plus 2 times the second place votes plus 1 times the third place votes. Let's just go one at a time. Let's start out with Mickey Mouse. 3 times the first place votes plus 2 times the second place votes plus 1 times the third place votes, and just push them down. Mickey Mouse has 10 first place votes, 8 second place votes, and 14 third place votes. If you multiply 3 times 10, 2 times 8, and 1 times 14, and add that up, you get 60. So Mickey Mouse gets 60 Borda points. Now move to Bugs Bunny. The structure is the same. Push down the first, second, and third place votes. Bugs Bunny had 8 first place votes, 16 second place votes, and 8 third place votes. So you take 3 times 8 plus 2 times 16 plus 1 times 8, and you'll find out that Bugs Bunny had 64 Borda points. And finally, go to Scooby-Doo, the same structure, push down the first, second, and third place votes. Scooby-Doo had 14 first place votes, 8 second place votes, and 10 third place votes. And 3 times 14 plus 2 times 8 plus 1 times 10 is 68. So if you look at that, Scooby-Doo had more points than all the others, so Scooby-Doo wins by the Borda count. It's really very straightforward, but you do have to be careful. And let's wrap things up by talking more about fairness. What makes voting fair? Here are some common sense fairness criteria. There are a lot of ways to look at this, but we're going to look at it this way. One is called the majority criterion, and it simply says whoever receives a majority of first place votes should win the election. Sounds pretty fair to me, right? That's one thing. There's another one called monotonicity criterion, and it simply says if a candidate wins an election, that candidate should still win if other voters change their votes to support that candidate. In other words, if a candidate can win an election and then something happens so that the candidate gets even more support, that candidate should still win. Well, that certainly sounds fair. The third is called the Condorcet criterion, and it says that a candidate who wins all the head-to-head matchups should win the election. Again, sounds perfectly fair. And finally, the independence of irrelevant alternatives criterion. And it says if a candidate wins an election, that candidate should still win in any recount in which losing candidates withdraw. So if you win an election and for some reason a candidate withdraws, any recount should give the same winner. If you think about it, all four of those criteria sound fair. And there are other things. We're going to stick with these four: majority criterion, monotonicity criterion, Condorcet criterion, and independence of irrelevant alternatives criterion. Four common sense things that seem to make an election fair. So you might say, whatever election method we use, it should at least satisfy those four criteria for fairness. If these fairness criteria are so common sense, why don't we just find a voting method that satisfies all of them and then use that method all the time? The answer is because it's not possible. It turns out, in a result derived from his PhD work in 1951, Kenneth Arrow proved this. Well, it's up to you to decide if it's surprising or not, but I would say this surprising result. And it's called Arrow's impossibility theorem. And it basically says it is impossible to create a voting method that always satisfies the four criteria of fairness that we just mentioned.